I think we were on question 5.
I think I may not have gotten that far, but yeah, that's fine.
I'm sure we discussed question 4. Why was
Mm.
logistic activation function a key ingredient?
Yeah, I do remember that. Yeah, 3 popular activations. I guess ReLU, sigmoid, and I don't know if they count steps, the heaviside function as a activation.
The step one, it's not popular anymore, right?
Mm-hmm. Yeah, it's definitely not popular. Oh, I guess the 10H one as well.
Yep, TANH is, I've seen TANH being used in CNNs, I think.
Sorry,
Yeah,
say
it's
again?
still used. I have seen TANH being used in CNNs.
Mm-hmm. Yeah, same.
They still
I think it's
use.
quite popular actually.
Yeah.
Yeah. Um, can I draw them? Yeah, sure. Well, I don't know how to. Yeah, right. Like the sigmoid is like an S shape going from 0 to 1. The tan
Yep.
H is like -1 to 1, also S
Yes.
shaped. And the ReLU is like flat up to 0 and then linear with slope 1
Yes.
after that.
Okay. I think we can move on to the next question. Suppose you have
Mm-hmm.
an MLP composed of one input layer with 10 pass-through neurons, followed by one hidden layer with 50 artificial neurons, and finally one output layer with 3 artificial neurons. All artificial neurons use the ReLU activation function. What is the shape of the input matrix X? That would be. Do you want to answer that?
You can go ahead. That's fine.
I mean, I don't want to do both the jobs. You can, yeah.
Okay. I was thinking like 10 times the bat size, or
No,
bat size
no, no,
times 10.
no. Batch size. Your input, your weight matrix is not dependent on batch size, right? Batch size can be anything.
Yeah,
Your weight matrix is always a constant. It does not vary depending on your batch size.
it doesn't, but they're asking for the input matrix, no?
Oh shit! Yeah, I was wrong. Yeah. Okay, I was thinking of the weight matrix. Yeah, you're right. It's batch size by 10. Yeah,
Yeah.
or 10 by batch size, whatever. Yeah.
Yeah, I don't know which way around. Yeah, this is.
What does it say in the answer?
Oh,
Okay, I think
sorry.
we'll check it at the end, right? We can finish all of
Mm-hmm.
these and okay.
Yeah.
What are the shapes of the hidden layers? Weight vector WH.
I guess 10 times 50.
Yep, yep. That should
Yeah.
be right. And bias is just 50, right?
Yeah.
Uh, no, I think it's the. Wait.
I think you're right.
Yeah, 10 by 50 and just 1 by 50,
1
right?
by 50. Yeah, I think so.
Okay, so the input size is 10 here.
Mm-hmm.
Okay. Yeah. What are the shapes of the output layers? Weight vector W0, WO, and its bias vector BO. Yeah, that would be 50 by 3, right?
Yeah, I think so.
And 1 by 3. Yeah. What is the
Yeah.
shape of the new network's output matrix Y? Yeah, that's again batch size by 3, right?
Okay. Yep.
Write the equation that computes the network's output matrix Y as a function of X, WH, BH, WO, and BO. You want to go for that?
Sure. Give me a second. So it should be like y is equal to your activation function, which let me call phi for now, x wh plus b h, and then multiply all of that by w0 plus b0.
Yeah.
Oh,
Yeah,
and then
I think
another
that's right.
ReLU. Okay. So another, yeah.
Yeah,
So
that's
I
right.
get, yeah, okay, cool. Yeah,
Can you take a look at the answers as well?
yeah, that's what it says. So part A was like m times 10, which where m is the bat size. The next one is 10 times 50 and 1 times 50, 50 times 3 and 3, m times 3 for the fourth part, and then yeah, ReLU brackets ReLU x wh plus bh w0 plus b0. That should be fine. Actually, I can, yeah, now both of us can't share screen. Cool, no worries.
Okay. How many neurons do you need in the output layer if you want to classify email into spam or ham? What activation function should you use in the output layer? If instead you want to tackle MNIST, how many neurons do you need in the output layer? Which activation function should you use? What about getting your network to predict housing prices? I think that's easy, right?
Mm-hmm. Yeah.
You want to go for it?
Yeah, I think if you just want spam or ham, it's just one output
Yeah.
neuron. And the activation function is a logistic.
Yep.
If instead you want to tackle MNIST, so that's 9, so you need 9 and then a softmax.
It's 10,
And
right?
oh, sorry, yeah, 10. 10 and then a softmax, and you just need 1 for the regression with no activation.
Yeah.
Um,
Yeah.
yeah,
I think
to
that's
email
fine.
it to, yeah, I think that's right. Do you want me to check it?
Yeah, sure.
To classify email into spam or ham, you need just 1 neuron in the output layer. Yep, typically use a logistic function. If instead you need 10 neurons in the output layer with the softmax function, if you want a neural network to predict housing prices, you need 1 output neuron with no activation function at all.
I think it's the same, right? I
Mm-hmm.
mean, it's all okay. Okay, we can move to the next question.
Mm-hmm.
What is back propagation and how does it work? What is the difference between back propagation and reverse mode auto diff?
I have no
So
idea
back,
about reverse mode or diff.
yeah, I've not heard of it either. I think
Mm.
reverse mode auto diff is what back propagation uses to calculate the gradients.
Okay.
It could be that. So back
Yeah, I
propagation
don't.
is,
I remember there was something about it in one of the chapters, but I really didn't understand that chapter. um,
is it one of the later chapters?
I'm not sure actually. I can check the.
So do you attend the Sunday sessions?
Yeah, but then sometimes I leave before
Not
the
Sunday, sorry.
discussion.
The yeah, okay. Hmm.
Yeah, yeah, I do it. I tend to vote the Sundays, and but it's not so great because like there's a discontinuity because sometimes they do different things on Wednesday and to us.
Yeah. So backpropagation is just the way you take your loss and then calculate all the gradients of the loss with respect to the weights, and then you update
Mhm.
the weights.
Yeah,
I think
that's right.
that's all backpropagation is. Reverse mode
Yeah.
auto diff is probably the technique that's used by backpropagation to calculate the gradients. Is that it?
Let me have a look. So reverse, and in the answer it says reverse mode autodiff performs a forward pass through a computation graph, computing every node's value for the current training batch, and then performs a reverse pass, computing all the gradients at once. So what's the difference? Well, backpropagation refers to the whole process of training an artificial neural network using multiple backpropagation steps, each of which computes gradients and uses them to perform a gradient descent step. In contrast, reverse mode autodiff is just a technique to compute gradients efficiently, and it happens to be used by backpropagation.
Yeah.
Yeah, so that's what you said, right?
Yep. Okay. Next question. Can you list all the hyperparameters you can tweak in a basic MLP? If the MLP overfits the training data, how could you tweak these hyperparameters to try to solve the problem? So there's learning rate
Mm-hmm.
and
The number of hidden layers.
hmm, and number
And
of nodes in each layer,
mm-hmm.
and I mean you could say dropout and all of that
Yeah,
stuff
also
with the
like your
L1.
activation functions, I guess.
Oh yeah, activation functions. Yeah. How could you tweak these hyperparameters to solve the problem of overfitting? I mean, you could increase your regularization,
Mm-hmm.
uh, dropout, and uh,
I'm trying to
uh,
remember. Do you, when you're overfitting, do you decrease your learning rate or increase your learning rate? Um,
I mean,
in,
I
decrease,
don't
right?
think
The
learning rate is it relevant to,
no,
like,
no.
if your learning rate is too high, uh, what happens is
You train too slowly.
no, if your learning rate is too high, you might diverge from the minima and get really high results.
Mm-hmm. Oh, okay.
If it's too low, it's, I mean, you would just need much more epochs to
Yeah, so you would
get at a
train
good
too
result.
slowly.
But is it actually relevant to the problem of overfitting? I don't
Maybe
think
not.
so.
Yeah, maybe not. So let me see what it says here. Okay, so the number of, yeah, the hyperparameters are the number of hidden layers, number of neurons in each hidden layer, the activation function, and in the output layer. In general, the ReLU activation function is a good default. In general, you want the logistic function for binary. If the MLP overfits the training data, you can try to reduce the number of hidden layers and reducing the number of neurons per hidden layer. That's the one it
I did think
suggests.
about this, but uh, I mean, it definitely works. But like, if you listen to Jeremy, what he says is you should use a complex neural net and then regularize your way out of overfitting.
Mhm.
You should not just
Yeah,
cut down layers. That's the
yeah,
solution he says.
yeah. I thought that would be better as well. Yeah, I think your suggestion of like dropout or like adding momentum or something would be
Yeah. Or batch
better.
normalization.
Mm-hmm. Yeah.
Okay.
Okay. Oh,
The
is that
last
it? Oh.
question, there's one more question. Train a deep MLP on, okay, this is a problem question. Okay.
Mm-hmm.
Train a deep MLP on the MNIST data set. You can load it using blah, blah, blah. See if you can get over 98 precision. Try searching for the optimal learning rate by using the approach presented in this chapter, by growing the learning rate exponentially, plotting the error, and finding the point where the error shoots up. Okay.
Okay. I guess we can spend some time till like I guess till maybe 10 to 6
I don't know what's that
or
in Indian time.
oh sorry, from like 30 minutes from now.
Okay.
10 to 11, I guess. No,
Okay.
or whatever. Yeah. 30 minutes.
Again, half an hour, right?
Mm-hmm.
Okay. Yeah.
Hey guys,
Hey
Gautam,
guys.
Maria. Sorry
Nice to
about
meet
that.
you, Scott.
Hey, hi
That's
Dinesh.
good. How are you?
I almost forgot that I have a one-to-one on a 5 o'clock.
Hmm.
Oh,
So sorry about that. And unfortunately, it's gonna be every every week. So
Oh, it's fine.
uh, I didn't realize when I was so excited about this 5 to 6. We may need to find other time. However, we have 20 minutes, so let's utilize those 20 minutes. Or uh,
Ac-
or have you been already doing something?
Yeah, actually we
yeah.
had to begin without you.
Oh no, no, perfectly fine. Share your screen.
No, actually we were doing the last problem, the coding question.
Okay.
So we were like in the middle of a 20-minute gap to do that coding question on our own, and then we were to discuss on it afterwards.
Okay. All right then. What time we are meeting back?
I think in about 15 minutes.
In 15 minutes. Then we'll have just 5 minutes left.
Uh, okay, then 10 minutes, I guess.
Mhm.
Let's meet in 10 minutes and then we'll have 10
Yeah.
minutes to discuss. Okay.
Mhm.
I'll talk to you
Yep.
then.
The last question.
Okay.
Or if you have any other thing you want to discuss in the previous
Yeah.
questions, we can do that as well. Because I'm
Okay.
actually done with the coding question. Even I mean, it's not
Oh.
much. I just, I just looked at the solution basically.
Oh. Okay.
Yep.
I'm fine with either way.
Okay, we can take 5-10 minutes more, and then we'll discuss.
Okay. Let's meet in 10 minutes. Okay.
Yep.
Cool.
Shall we start discussing?
Yeah, I'm good too. Didn't get 98% though, going very close.
Okay, were you actually coding it by yourself?
Well, yeah. Well, I was following the example in the book with the fashion feminist. I didn't change anything, so it was not like it was difficult.
Okay. Okay. Do you want to share?
Sure. I can't tell you that it's good.
Is it?
I mean, I don't want anyone to think that it's good what I've done. I think this is like following. If you guys can see, what are you guys looking at?
The collab, yeah.
Okay, cool. Yeah, so I just started with like the MNIST and went the same way as with the fashion MNIST example in the book. So, load your data set, look at, split it in almost exactly the way. So like the first 5,000 are your validation. I just kind of made sure that they weren't all like fives first or whatever, and built the model exactly the same way. And used the sparse categorical. I thought here it should be precision because they said see if you can get over 98% precision, but I guess they still meant accuracy because if you try precision in there, it gives you an error.
Could somebody explain to me what is sparse categorical cross entropy?
So he says somewhere along in the book, it's just categorical cross entropy when you're like y looks kind of like this, as opposed to like a one hot encoded. If it was like one hot encoded, you would instead put in categorical cross entropy here. I wasn't too clear on what his example was. Let me find it for a moment.
So are you saying when it if we are predicting if we are getting the probability in a one hot encoding, we go for a categorical cross entropy, and then if we are getting into probability of
It
number.
depends on how your labels are given.
Mm-hmm.
So if suppose you have, so in this case you have 10 classes, right?
Yeah.
So if the labels were given as one hot encoding, as Maria said, if it was 001 0000, and if the labels were given in a one hot encoding format, then the loss is uh, simply categorical cross entropy. Here we are given the actual indexes, right? 5, 3, 2, 1.
Yeah.
So here the calculation of loss is done using sparse categorical cross entropy, but the actual value of the loss is the same. It doesn't matter. It's just depending on the way it's there in the data set.
And why it's called sparse? Is there
Good
any
question.
Because it's it's stored in a sparse way, right? Instead of having a huge one hot encoding of 1000, I'm just storing the number at which the one is present instead of having all the zeros.
Is that what that meant? Okay, cool.
Yeah.
in a sense?
I mean,
No.
that's what sparse means in the normal. Suppose you have a huge matrix with lots of zeros and values only in a few places.
Yeah,
You store it in a sparse way by not storing all those zeros.
that's
By
correct.
just
Right.
However, how does this sparse come into picture in here? So we have given the label in the form of not a hot encode, but
I don't think there is any sparse storage or anything in there. It's just called sparse because it's similar to that, right? Instead of having one hot encodings, you are just having the numbers. I mean, you've already done the sparsification yourself.
Mm.
That makes sense.
now I'm not getting you. I understand what is sparse, but I'm just trying to connect the.
Your Y labels are already sparse, right? Instead of having a huge one hot encoding matrix, you are having a single vector which represents your Y. So you
Yes.
have made it sparse. Hence, the loss is also called sparse categorical cross entropy. This is my best guess, by the way.
Oh, the sparse would be the if we have a one hot encoding vector.
No.
That's
You're
more a
making it.
sparse.
No,
Yeah, I see. I think, Dinesh, what you're thinking of is like a sparse matrix is a matrix that has loads of zeros, right?
Yeah, exactly.
But that's technically, I guess what Gautam is saying is that if you had a one hot encoded matrix, if your Y matrix is one hot encoded, then it is a sparse matrix. But a better and if you had it that way, you would use categorical cross entropy. But if you had turned it into a vector that only stores the position at which you have the ones, which is the way you have here, right? Then you would use a sparse categorical cross entropy. So just so like the compiler knows what sort of format you're expecting. I think that's all.
Yeah.
And
Okay.
Dinesh, what you told is not wrong technically. Yeah. If a matrix
So-
has lots of zeros, it's called a sparse matrix.
Yeah.
We are just yeah.
So you're saying, okay, so what I'm gathering here is that if you have given like a non-hot encoded vector, like if you don't given, so it's just the inverse. If you have given the vector of actual labels, then you're going to use this sparse categorical cross entropy. Perhaps it's going to create that probability of a sparse matrix in somewhere. I don't know. I'm just trying to.
Maybe in the backend it converts these into ones and zeros again. Yeah,
Probably,
that's possible. Yeah.
I doubt that though, right? Because like you can just compare directly then. I mean, you don't need to, right?
That's true. Yeah. That's true actually. Yeah. Yep.
Because
You
like
can
your prediction will also be just a
you just
vector
have to
like this.
Yeah. You're totally right. Yeah. You just
Yeah,
have to
well,
take the probability at the fifth position. See, yeah.
Oh, maybe. Although
that would be like you will get the probability for each number. So you will get the probability of each each label.
Yep.
Then wouldn't we convert that into like would that be the final stage, or does this convert into one hot vector finally eventually? Because no, labels are there. I take back
Maria,
what
can
I'm.
you just open the formula of categorical cross entropy on Google? On Google. Yeah.
We need 1 hour every day.
Yeah. Is this the documentation? Yeah.
Okay, can you just open the normal formula? You don't have to go to Keras.
Oh, sorry.
Yes.
Surely there's a Wikipedia article somewhere here.
There is a question why up there, like there was, I saw why binary.
Oh, why? But you mean this one?
Categorical cross entropy, but are we looking at sparse?
Yeah.
You just don't have the formula, right?
Sorry, yeah.
Okay, so let me just Google it.
Okay, let's have a look. Oh, it's not a.
Yeah, this is the one.
Okay.
Okay, no, I think no. This is
It's
too complex.
very mathematical. Yeah. Oh, this might be a good one.
Yeah. Yeah.
So go on.
Yeah, go on. You can go on.
No, go for it.
No, I was just trying to reiterate your point that we don't need the whole one hot encoding. So cross entropy is basically summation of yi times log yi. So log yi is basically the predicted probability, right? So your yi, sorry, log of y cap. So the yi is actually 0 at all the positions except for the index where the value is 1. I mean,
Correct.
except
Yeah.
for the actual value, right? So you don't have to convert that index to one hot encoding again, because you know that only the fifth one matters. So you would just take the fifth probability value predicted by your model, that's y cap I.
Yeah.
You take up the log of that and then you multiply it by 1.
Yeah.
That makes sense?
Yeah. So that is categorical cross entropy.
Yes.
So where you have given the target in a one hot encoded.
Yeah, I mean, even in sparse,
Yeah.
my point is, if you are given say 3 or 4 or 5, you don't have to convert that 3 to one hot encoding again. You can, what you can do is, because so if you convert 3 to one hot encoding, what you're getting is 0 0, then 0 0 0, then 1 at the third position,
Yeah.
and then a bunch of zeros again, right?
Correct.
So uh, when you calculate this loss, the value of yi is 0 at all positions except the third position, right?
Correct.
So what you can do is just calculate log of y cap I at the third position, which is the probability predicted by the model at the actual label. I mean, at the actual node, the actual, I mean, the
Yeah, the
true,
actual class.
yeah,
Yeah.
whatever. Yeah, I'm bad at this. Okay. And then you multiply that by 1.
So you're saying because the reason you're taking 1 is because that's you're multiplying the max probability which is predicted. So obviously your model is going to predict the probability for each number. So what do you mean by the third position is the maximum probability given by your model? You just take that.
Only if it's correct, right? So like technically, like if you look up here.
Yeah.
Oh, hey guys, sorry about a little bit delayed.
Okay.
If you like look up here, yeah. I mean, if it was a bad model, technically this could be the 1, and then you'd be taking the log of this number, right? If you know what I mean.
Yeah. Okay. I'll look it up actually. So I may ask on next Monday just to have more clarification on it. So
yeah.
Thanks, guys.
I have a doubt between. I mean, like I think I got the intuition what's going on, but it's just a little bit more going into detail what's going on there, and to have a good understanding of it.
Yeah.
Sorry, Arshad, we were having actually.
Oh, no worries. It looked interesting. You're trying to understand cross entropy,
yeah.
are you?
We are having this homework sessions as well.
Yeah.
Oh, right.
So what we are having a one homework session on a Monday, 5 to 6. And we thought the Monday went really nice. So we thought we will catch up today again between 5 to 6.
Cool. Yeah. I guess we're recording them. I might watch them because unfortunately it's commuting time for me in that time. But yeah, no, really cool.
Yeah.
Are you commuting, Arshad? Have you started? Oh, you were always in the office, weren't you?
Yeah, basically the older office, I used to stay until 9:30, 10 and get a taxi home. But the new one is a real pain. It's in the middle of town. So I'd have to walk well, it would be a pain to get a taxi. So I'm using public transport, so I'm having to leave earlier.
Yeah.
Cool. So today we're starting our first session on the convolutional neural networks section. Let me see if I can. Unfortunately, this is my Linux machine, so we'll have to get used to this. Okay. So I was thinking if we could start reading it from the start until this these CNN architectures up to SENet, if we can do that. The guys on Sunday might be a bit slower and they might redo this, and that might be worth doing anyway, because a few of these architectures are actually quite involved. So,
Yeah.
I mean, you can get an overview of them, but you won't be able to really understand them in a lot of detail, unfortunately.
Just to add that for this chapter, we have at least 2.5 weeks. So because I think 4 lectures on it, and
oh,
it is
fantastic!
A holiday.
Okay.
Yeah. So just pace-wise, maybe if we slow down a bit.
Yeah, for some weird reason, I thought it was going to be. Okay, so let me share it with me. That would be fantastic, because I'm actually really interested in this section.
Yeah.
And I was afraid that we didn't give it enough time, and I was like, this is a really important section. So we're doing computer vision. Yeah, so we're doing it today, and then holidays next Wednesday. Then we're doing Sunday. Yeah, fantastic. So okay, then we don't have to rush this thing.
Yeah.
If we get up to the pooling layers, finish off the pooling layers section, which is the up to this guy, and then the CNN architectures, will probably take a whole session, and then the other bit can be 1 or 2 sessions as well, because it's got object detection stuff as well in it.
Yeah.
Is that okay?
Yeah. Is the pooling section including?
Yeah, so we're including the pooling section up to CNN architectures. So we're not doing that bit, but up to including the pooling. Yeah.
Cool.
Yeah, so we'll catch back up at about 6:45. So I guess I'll see you guys in about 40 minutes.
Yeah, cool. See you then.
Okay, thanks then. Oh, hey guys. I guess we'll give people until 50 minutes past to get back.
Okay.
Sorry, excuse me. Had a bit of a burp there. Oh, hey, Purusha. We're just going to wait until 50 minutes past, just in case anybody else is coming in.
Right. Okay, cool. No problem.
How goes the world of reinforcement learning?
Going okay. Going too fast for my liking.
Yeah, it's I subscribe to this feed, which is this kind of a summary of papers in AI and kind of I think it's papers with code as well. So,
Yeah.
but anyway, I get about like 75 a day, and out of those, I'm sure it's about 5, 6 every day that I'm like, I've got to read those. It's ridiculous the amount of work that's being produced.
But it's a paid subscription, right?
Sorry?
No, this one isn't paid. It's let me see what it's called. It's
because I saw recently one.
it's something. Pardon me, where's probably my. Okay, so it's called Paper Digest is what it's called.
Okay.
And yeah, so code and data. So it's, I don't know, it promised to give me a summary, with a little bit of an abstract for each one.
Mm.
So I thought, okay, well, that sounds good because that'll be easy to parse, but it's still like 100 a day.
Mm.
Okay, so getting back to where we were, so because I don't want to waste any more time. Yeah, so we're looking at convolutional networks, mainly used for computer vision, but they have actually got applications in other areas, such as natural language processing. So I'm not sure if Jan LeCun, who's one of the people who was one of the first to use them actually for image recognition, actually had his basis, because I haven't read his original paper. But there's been quite a lot of research on how the human brain itself processes visual information. And as early as sort of the 1950s, quite a lot of experiments were done on animals. And one of the discoveries that was made was that certain neurons were highly sensitive to orientations of lines in the visual field. And that kind of gave sort of a clue that perhaps, those were the building blocks then of used by higher level neurons to sort of build features, and then, and from then on to actually build a picture of the image that was being seen. And one of the interesting things about the human brain is actually your visual system is highly hardwired. It's a few of these systems where you can quite easily fool it because it's hardwired, and you've probably all seen these visual these visual tricks. And unfortunately, if it ever gets damaged in any way, then it's very unlikely that it will ever repair itself, really, because of the way that it's actually kind of structured and the way it works. We don't still fully understand every aspect of it because the human visual systems got a lot of feedback, and none of what we're going to describe here has any feedback, but it still does amazingly well on visual recognition, and sometimes actually, it's superhuman. Yeah, so this is a little bit of the history of it. Okay. Yeah, and although we're only going to be looking at vision today, but they have been used for other tasks such as voice recognition and natural language processing. And it's interesting that they've been used in this way because a lot of the current models for natural language, I'm going to digress here just for 1 second and put my own little pet theory in. Actually, let's just go a little bit forward. Yeah, is that convolutional neural networks look for certain features and have filters that do that. And natural language is actually not just a set of words. In some ways, probably a better way to process natural language is actually create a parse tree and actually use the tree as the mechanism. And attention, which is one of the modern kind of NLP, if you're into NLP, is kind of a little bit like that, but it's not a full tree. It's only got limited amounts of dependency. It doesn't fully capture the full dependency that you get. But anyway, long story short, instead of requiring the input to a neural network just as a flat array of data that you just kind of push into a network, we're now sort of looking things at more as like two-dimensional in the way that images are, like they're projected at the back of your retina, or even as just photos, in an image program. And that's the kind of thing about convolutional neural networks, is that they've got this notion of this two-dimensionalness of the data that they're looking at and the features that they're extracting from that. Okay, so so convolutional neural networks have been used for object detection, and this is kind of vision-related stuff, and then semantic segmentation, which is actually classifying individual pixels. But of course, they're used for sort of self-driving cars and lots of other applications. So this is a little bit of a history of the research that was done on animals and their visual systems. And the discoveries that were made were that because scientists can actually measure the output of individual neurons since the late 50s and early 60s, they could tell that a particular neuron was sensitive to the image within a small region of the retina. And this is what's called the receptive field, or the local receptive field. And that the receptive fields of different neurons could be overlapping. And the idea is that, and then obviously these overlaps could then build more complex structures. And one of the critical things they showed was that it was possible for certain neurons to only react to horizontal lines, while others reacted only to other orientations of lines. This was not known sort of before as to how specialized individual neurons were. And it was kind of this research which showed that actually neurons were highly specialized to different aspects of the actual input. And that kind of then later motivated these convolutional neural networks. And then we've got this aspect of where some other neurons actually seem to sort of accumulate data from these local receptive fields to get a larger receptive field that they actually apply themselves to. So this is just a little bit of a history about the research on human vision system and our current understanding of it. There is quite a good course actually on YouTube if you're into this area. It's by a center called the MIT Center for Brains, Minds and Machines. And some of the professors who were kind of involved, not in this research, because this is quite old, but the research in the early 80s and 90s into the visual system. It's actually quite a nice course that covers kind of what the current state of the art is in terms of what we know about the visual system. So if you're really interested in it, that's worth knowing. And I could probably provide you a reference to that if you're interested. And yeah, so this is kind of a picture of what they were saying, that our current understanding of the human visual system is. You've got these low-level neurons, which are very sensitive to particular orientations and within particular regions of the visual field. And then you've got these mid-level neurons, which accumulate the data from these lower ones to create sort of slightly more complex shapes, again, quite abstract. And then finally, you've got neurons which actually can understand, which actually represent, actual proper concepts or proper objects that we're actually interested in recognizing. And one of the most famous papers in this area is the paper by Jan LeCun, and he introduced this architecture called LENet5. And MNIST, which you probably all heard of, which is this image data set for recognizing numbers. He actually was the guy who I think created that data set. Yeah, he created that data set, and it's from his website. You can download it actually. And he's the guy who invented this algorithm which classified it and was actually used commercially by a lot of banks to recognize numbers on checks. His architecture introduced these things called convolutional layers and pooling layers. Okay, so there's a little digression here on asking, do we really need convolutional layers? Can't you just have a fully connected network that will do the job? And actually, in theory, yes, that will do the job. But the only problem is that you will have to have a really horrendously huge sized one. And they give an example here that if you have a 100 by 100 pixel image, then that's got 10,000 pixels in that image. And if in the first layer of your neural network, you've got 1,000 neurons, and you're connecting this input to those 1,000 neurons, then that's 10 million connections already. And we're not even going any further down into this deeper layer that we would need. And you've actually lost quite a lot of information by already compressing those 10,000 pixels into 1,000, using the 1,000 neurons into, because they'll actually output one value. And convolutional networks basically solve this kind of problem because we know that we're not applying any arbitrary function to the input data. We're applying specific type operations that we're interested in for vision, and convolutional networks make this more tractable for us because we're now implementing a completely generic solution. We're doing a particular problem, and CNNs basically help us with this. So is everybody okay so far? I don't know if anybody's got any questions.
Just one question with regard to this DNN. Somewhere down the line, they say that DNN would learn only the specific area. You wouldn't able to apply what you learned on one area to another, and a CNN can apply, can learn from one part and can apply that learning on the other part. I read somewhere. I don't fully understand. Like logically, yes, but technically,
Yeah. So basically, the issue is, I mean, let's say you had an image. There was something in the top left-hand corner of that image, and then you trained your network on that. Then the weights that were connected to that part of the image would get activated. But now, if you rotated it so that the data was in a completely different area, that training would no longer work, because the data is now in a position where the weights have never seen that. Do you sort of I don't know if I'm kind of explaining that.
yeah.
So a network so it's a bit like you've never the network has never seen the data that you're trying to use it on, basically, because you only trained it on that one orientation. Because of the way convolutional neural networks work, they've got some aspects of the fact that you could translate and rotate things within sort of reason. You can't arbitrarily do it, but they have got this additional feature because of the way they work, that the data, they could work on data they haven't seen before, because it's very similar to data they've seen before, but just maybe translated or rotated a little bit. Yeah.
Okay. Yeah, makes sense. Yeah.
So now we come to the actual description of the convolution layer. Okay. So the most important building block for convolution CNN is the convolutional layer. Neurons in the first convolutional layer are not connected to every single pixel in the input image, like they were in the layers discussed in previous chapters, but only to pixels in their receptive field. So we'll see a diagram of it in a little bit. In turn, each neuron in the second convolution layer is connected only to the neurons located within a small rectangle in the first layer. This architecture allows the network to concentrate on small low-level features in the first hidden layer and then assemble them into the larger, higher-level features in the next hidden layer, and so on. Okay, so what is all that on about? So let's say that this is the underlying image that you're trying to process in 2D. Basically, a convolution is what it does is it takes a small area of the image, applies a function to each individual pixel. So so imagine each individual pixel here is being given a weight, and then the overall value is computed and then stored here. And then the next layer is basically taking each of these individual values and computing a function of that, and then generating the output on there. So what's happening here is that, for instance, this guy is perhaps recognizing some very high level features. For instance, you can make it so that this particular layer only recognizes these vertical lines, so that neuron over there will only get activated if there is some verticalness in the underlying image. And then what you could have is that this layer is got, and then you could have some other which are sort of more active towards a line that's sort of in that angle, and some which are in that angle. And what that means is that this layer will have accumulated quite a bit of that kind of more information about the raw image. And now your next layer, which is taking this area here and computing a function of that can then generate something more abstract, which is saying, well, there was a line here, and there was a 45-degree line here, and there was a half a circle here, and then that could actually say, oh, okay, that looks like a ball, or that looks like a like a house, or something like that. I mean, that's a little bit too concrete, but that's kind of the idea. Does that kind of make sense, or is that I don't know if anybody's got any questions about that, because this is the critical bit. The convolutions take an area at each point.
Just one question. Makes sense. So the feature which we're going to pick up in a convolutional layer 1, do you call them higher level features or lower level features?
So layer 1 is low level features. So these are just individual lines, or I mean, I'm making the assumption it's lines. It could even be not lines, but they're really just things that you would notice in the image in a small area. It's the higher level layers that have got like information about the whole image or much bigger parts of the image.
Okay.
Yep.
Yeah, so the input layer, all the layer we have receptive field in the input layer, or only sub fields that are receptive fields?
Sorry, Shem, so I didn't quite understand your question.
Yeah, so in the input layer,
Yeah.
they say they mark the receptive fields, right?
Yeah.
So my question is, at the input layer, do we have all the field in the input layer to be the receptive fields?
Okay, I think I know what you're asking. So let's say that this image is the input, yeah?
Yeah.
You know, the whole image, so the full 3D, yeah, sorry, not 3D, full color image, yeah?
Mm-hmm.
What the convolution does is it starts, say, at some corner of that size and compute a value, and then it kind of walks the image all over.
Mm-hmm.
So it's not that it's only looking at, you know, the convolution won't just look at just that bit of it. It will actually look at every part of the image, but it kind of summarizes the area in you know, when it computes the value at this level, it's kind of like whatever it's, if whatever calculation is doing on these pixels, and then it sort of walks that so that, you know, the values that you're getting here are starting from over here, say, and then as you walk this convolution across this, you know, this area here, the values are getting filled up, and then it starts on the next row and does that, and then on the next row it does the same thing, and then all of these values are kind of getting filled up. So actually it will be across here, won't it? So for instance, if this bit here was kind of in this corner, then it will be values in here that will be getting filled in.
Okay.
Yeah, and then as it walks it, different values in this layer will get filled in. Because this layer, at least depending on how you've configured it, currently this layer is the same size as this one, but there are ways to make that layer smaller. We'll see them later on. But the main thing is that it will look at the whole image, but small parts of it at a time to compute the values in here.
So the small part is a function of the larger part of the layer, right?
Yeah. Yes. Yeah. And this is the bit where they talk about this weight sharing idea. And what they mean by that is that, you know, let's say this, you know, this particular area here, we're applying some sort of function to it to compute this value up here. Well, we're going to apply the same function on every area here, yeah, and that's why. So the weights are actually the weights are in this function here, this kind of whatever it's doing to convert whatever that guy is into this guy. But it's going to use the same weights each time it applies it, so that, you know, different parts of this image are not going to have different weights. They've got a different mechanism to do that, but a particular convolution operation uses the same weights across the whole image as it walks it. Does anybody kind of understand what that means, or is that still really confusing, this weight sharing idea? Because that's really critical as well.
Can you go on one more time, please?
Okay, so imagine we've got this area of the image and we're applying some sort of function to compute this output, yeah? And that function is basically a weighted, you know, sum of the pixels in here with plus a bias. Yeah, so it's a bit like a neural network. You know, each individual pixel in here is kind of, you know, is connected to a little neuron, and the whole thing is sort of computed, and the sum is produced here. So the weights that we had in here, all the different weights for each of the different pixels, for one particular convolution, that those weights are kind of fixed. And then as, you know, this window kind of moves across the screen, exactly the same weights are used at each time. They compute different values because different pixels are here, yeah? But the weights themselves are the same. And this is what they mean by weight sharing. And this is why it's more efficient to do it using a convolution, because, you know, for instance, this area will not have different weights to that area. The weights will be the same, but the underlying pixels are different, so the values that come up here will be different.
Yeah, makes sense.
Okay.
Yeah.
They're going to sort of redo it again.
Yeah.
So Yeah, so that
just one question. I think it's going to come later on, but let me ask in advance. So when we have the kernel of like 3 by 3, and then I think at a later stage we say we're going to have the kernel of like a 4 by 4 or 5 by 5 as well. So you're going to have a multiple kernel on the same plane.
Yeah.
Would the weights and biases are still going to be same, or they are based on the kernel?
So the weights will be based on the particular that kernel. Yeah. I mean, I'm assuming when we say kernel, we're talking about a particular. Really, we should really talk in terms of filters, actually, because a particular filter has a certain weights. It's got a certain kernel because it's say 3 by 3 or 4 by 4 or 5 by 5. So that's the filter, and it'll have some weights in it depending on how big. Well, if it's 3 by 3, then that's nine weights, isn't it? Plus one bias. But the weights in there will be the same for that filter, even though it moves across the whole image. Yeah.
So the kernel itself, like, okay, so you're saying the weights are there. So in a sense, like the kernel is usually where you have one line where you have ones and then rest are zeros. So those are the value of the kernel itself. So that means that's not the that's not the parameters. So there are like a separate weights and biases associated with that kernel.
No, I think that we could regard that. I mean, I'm slightly concerned about the use of the term kernel because I'm not sure if that's the right word. It might be.
Let's
but
call it the filter.
Yeah. So if we call it a filter, and then let's say the filter is looking for those vertical lines. Yeah. So you've defined it using that. So what that filter will do is its weights will be the ones for the vertical line, but it will apply it across every single area on the image, looking for vertical lines, but it'll use the same values for the weights.
Yeah, but the value of the filter is different than, because filter, we're going to have, let's say 3 by 3 example of the filter. And if we are looking for a vertical line, so we're going to have, let's say, the middle column as a ones, and then two side columns as zeros.
Yeah.
That's not the weight.
That is the weight.
Oh,
because that is the value. So basically, when we just said it's going to have zeros on the two sides and a 1 in the middle.
Yeah.
Those are the weights, because that's what you're going to multiply the pixels by, because you'll multiply the middle pixel by 1 and multiply the outer pixels by 0 and add them all together to compute what that guy is. So yes, that is the weight. Yeah.
Okay. So would those weight get changed, get trained, or they are fixed during the training?
No, this is critical, is that they're learned. And that's why the convolution is implemented as a layer in the neural network. So no, you don't have to tell it what the weight should be. All you need to do is give it the input image, tell it what what the objective is, and then using back propagation. And because the convolution operation is one of those that's supported with back propagation, it will learn the correct weights to apply. Yeah. The hyperparameter to do with the size of them, like whether it's 3 by 3 or 5 by 5, that you do have to define. But the actual weights that you should use, they will be learned.
Okay, so they are not just constant ones or zeros. They are some fractional value learned by the network itself.
Yes, that's right. So it's up to the network to decide what features to detect to actually generate the overall objective that you're trying to achieve. And that's the critical bit, because we don't know what those values should be, for any particular task. It really has to learn them. And that was sort of the breakthrough, was that this convolution operation, you could apply gradient descent to it and back propagation to achieve this end-to-end training of it, even with the deep network, because there's multiple layers of the convolutions being applied.
Yeah, makes sense. Thanks.
Okay. So there's a little note here saying that convolutions are reasonably easy to understand, because you've got this notion of a 2D image, a convolution is being applied, that this value was computed from this area on the screen. So in some sense, they're reasonably easy to interpret as to what's going on. And I think, yeah, I don't know if any of you have seen the different convolution layers. You know, there's some online simulators which will show you what the different layers are. And you can see at the earlier layers, it's just lines, and and later layers, more higher higher dimensional features get picked up. But yeah, this is an interesting, because a lot of time neural networks, you don't know what the weights are and what it's doing. But at least in this case, it's reasonably easy to interpret that the value from here was derived from this receptive field in the image. Yeah. Now they've got a little bit of a description about exactly the operation that's is going on, and this is where this is a 3x3. So the idea is that it does that operation, generates a value here, and then it walks one to the right and does exactly the same thing and fills in the next value. And there's a couple of things here that we need to understand. One is this thing called padding. Now, the problem is the problem that padding is trying to solve is that images don't always have to be an even size or an odd size or to match the kernel that you're interested in, because this guy is kind of, say, walking. It might be that if you go with 3x3x3, you end up having to look at a pixel that's actually not in the image anymore. And it's a question of how do you solve that problem? And they solve that problem either by not even looking. Basically, we'll see the code in there later on, but you've got two options. You can either pad the image with some additional zeros, so that when it comes to the end here, for instance, because this is a 3x3, when it comes here, it will do this 3x3 area here as the final one. And it'll use these zero paddings as part of it. Or you could tell it, well, basically, you got to stop here because you can't go any further, because you would kind of go off the image. So yeah, these are parameters that you need to consider as to what padding, or whether you need padding or not, because adding padding means that you've added some zero data on the edge, and I don't know if that's any good for you. If you don't use padding, you might lose sort of like a whole column or row of pixels, because your kernel can't actually get there with the way that you've defined it. Does that make sense about what padding should be used for?
Yeah, just to add that on the here we are padding, I think, zero padding,
yeah,
or not padding. In a fast AI, what he does is like he just pad with the same value, I think, which are value.
Yeah, I mean, there's lots of things you could do, the average, but I think here, yeah, you've got loads of options. Yes, that makes sense. There's this other notion as well that's worth knowing called stride. And so if stride is basically, let's say that you've done this area here, and now you want to know what to do next. If the stride is 1, then you would just walk 1 forward and kind of redo the whole thing. If the stride was 2 and you were here, you would actually walk 2 and then redo it here. And you might think, well, what's the point of stride? Well, one of the nice things that stride does for you is that it really compresses the second layer down, because imagine if you were at each step walking 2, well, you're going to halve the amount of data that's needed here, because because you're stepping 2 every time. You don't need as much data here. If it was 1, then this would be the same size as you've got here, because each individual row and column would be walked like that. So yeah, I mean, that's the other important feature you need to know, is kind of stride. Does stride make sense to people, or is it kind of confusing as to what that is?
Fine with me.
Yeah, as I say, and the main use for stride is this compression. That's the reason. I mean, because stride is kind of destructive, which means that you're skipping over. For instance, if stride was 2, and you started here, the next one would be starting here. You missed this one out. I mean, you've included in this first calculation, but you have missed it out in the second one. So it is destructive, but it is nice in that it does this compression for you. So that it might be that it's useful because it's kind of you are losing some information, but perhaps it's not critical, but you have to do a lot less calculations at this layer. Okay, so that's that.
One question with regard to stride. So it's not that we are allowed to do just one stride, one kind, like either 2 stride or 3 stride. You can have same filter applied maybe 2 or 3 times with the different stride to get the different feature map.
Okay, so we're going to come to that in a second because the architecture is a little bit more complicated. I mean, here, for instance, we've just got one filter, haven't we? We're doing something, and we're doing that here.
Okay.
The real convolutional networks are a little bit more complicated because basically the problem they're trying to solve is that, let's say this was the image, and then you looked at this area and you computed that, and then you looked at this area. The problem is that you potentially, okay, fine, you picked at some feature here, but then there's probably lots of features in here which that one particular type of filter could not pick at. For instance, this was a filter that only did vertical lines. Well, what's going to do horizontal lines if that's the only thing you ever did to the input that you had? Mm-hmm. So in real life, actually, they apply multiple filters. So one might be doing vertical lines, another might be doing horizontal lines. But in one particular kind of batch of them, the parameters have to be the same because they're generating the same kind of shaped output. But you could have another layer of convolution, and the shape of that and its stride could be completely different. But within one particular kind of batch of them, they've got to be the same. Is that kind of confusing? Because we'll come to it, actually. They've got this notion of 3D, and it'll make a little bit more sense as to why all the ones within a particular kind of, within a particular, I'm not quite sure what the technical term is, we'll come to it in a second, but they're all the same. But you could have like multiple layers of them, and then each layer could be all completely different. And in real life, they are different. Yeah. Okay, so that's stride. So this is kind of slightly more mathematical description of what's happening if you have got a stride, exactly how the pixels are being picked up. But we're going to come back to it in a second because they've got even more.
Arsha, so the stride, do we perform the same stride at each layer, or we can alternate the stride?
Okay, so let's assume at the moment that convolutions are kind of like this one. Let's say that's one layer of convolution. And then on top of here, you have another layer of convolution. Then the stride here can be different from the stride up there. Yeah. So all the strides across, the whole network don't have to be the same. They can be different in different layers, yes. But as I said, there is this complication where this one input actually generates multiple convolutions in one go. And there the strides have to be the same. All the parameters have to be the same because of the way it works. We'll see that in a second. But then you can have a second layer of all of those, and then that can be doing its own thing. But yeah, we'll see in a second. Yeah. So this is so the notion of a filter. So a neuron's weights can be represented as a small image the size of the receptive field. Yeah. So imagine that the weights of it of this filter were the values that we have here. So that's a filter. So two possible sets of weights called filters or convolutional kernels. So this is let's have a look at 14.5. Yeah, so we'll get to that in a second. Sorry. Yeah, we'll get to that in a second. The first one is represented by a black square. So here we go. Neurons using these weights will ignore everything. So depending on how the weights are kind of defined, this is where, for instance, if the weights were like 1, 1, 1 here, but 0, 0, 0 on the other side, which is what Dinesh was saying a minute ago, then this filter is going to be really sensitive to vertical lines. It won't care that much about horizontal lines. So if there was a line that was completely horizontal here, that would actually produce 0 for that because it would be multiplying, these 3 values together, and those 2 would be 0, and that would be 1 if it was a horizontal line. So, so filters can become sensitive to certain things in the input. Yeah, so this is an example of one, and they show an image of here. So this is one which is very sensitive to vertical lines. It's a little bit hard to interpret, but you can see that the vertical lineness is something that's kept in the output, whereas horizontalness is not. Whereas this one, more horizontalness is kept, because this filter is more sensitive to horizontal lines, the horizontalness here, and it's not as sensitive to vertical lines, because the verticalness is always a little bit blurred, whereas the horizontalness is a little bit more sharp. And this was the original input that the two filters were applied to. So the next section, this is the bit that I was kind of just saying about, which is confusing, which is the stacking of multiple feature maps. So it says, up to now for simplicity, I've represented the output of each convolutional layer as a 2D layer, but in reality, a convolutional layer has multiple features. You decide how many, and outputs one feature map per filter. So it's more accurately represented as 3D. And so this is where, for instance, you could have that has one filter, this has another filter, you could have another 100 other filters in a convolutional layer. So that basically the output of them will be one output will be this guy, one output will be this guy, and one output will be this guy. And the reason you want to do that is because you want to capture as much from this as you possibly can. And because each filter is only kind of capturing a certain type of information, you can't, you've got to put in as many filters as you need to pick out the features that you're interested in here to be able to do further processing later on. So this is this concept of stacking. Does that make any sense to people, or is that a bit confusing what stacking is all about? And this is the bit where we were just talking about as to whether, if you've stacked these two, can you have different strides and different kernels for them? If you've stacked them, then you can't. You have to have the same kernels and the same strides within them. And this is all to do with the way they're defined. And so all neurons within a given feature map share the same parameters. So that's one filter, which is same as a feature map. Neurons in different feature maps use different parameters. So this is where we had like the parameters for this one are different to this one. So even though these two might be stacked together to produce like these two outputs, the weights for this one are different. All the weights for this one are the same, but they're different from the weights for that one. And obviously you could have 100 different of these guys, and they're all being learned, and hopefully detecting completely different aspects of the original image to help you to classify it. So I don't know if that, does anybody have any questions about that? Because this is kind of like this is like the trickier aspect of it, where you've got this stacking in 3D of the, you've got, say, the base image that your original input is, and then you're applying 100 filters to it in one go on the input to produce these 100 features. And each one of these is this convolution that's being applied, and then that's the output of that first layer, 100 of those, and then the second layer might be another 100 of those because they're being applied to the ones in the first layer. But the two eventual, these two could be different, but within a particular stack, they all have to be the same. Does that make sense?
Question on this. So basically, if you have the same filter, if you apply a same filter, as we are saying, if you want to stack up the feature map 1 and feature map 2, so the filter need to be same. So what's the difference then between the two filters then?
Okay, so the filters themselves don't need to be the same. Their shape and their stride has to be the same, but the weights that they have in them. I mean, if you go back to this example, I mean, let's say we stacked these two. They're exactly the same kernel size, say 3 by 3. This one's got weights for a vertical line. This one's got weights for a horizontal line. They both apply to the input, but this one produces something completely different to that one. So the filters can be different, but just some aspects of them have to be the same. The size of the kernel and the stride has to be the same, but the weights that they have inside them, they can be different, and that's why they detect different features.
So we said the weights are going to be learned by the network itself. So
yes.
We are not setting that up.
Yes.
So we are just saying like 10 filters of like 3 by 3. So network will go itself and try to make these 10 filters with the different weights now. It's not going to, we didn't say it like, okay, don't duplicate it. So where does it not duplicate the same weights across the board?
Well,
Because
that's a
I was
very
trying-
interesting question. And it must be to do with the pooling layers and other layers that we have that, because the network is learning from end to end, that, all 10 filters are not doing exactly the same thing. There's a couple of ways that this is potentially happening. First of all, the weights are not all set to 0. They're probably randomly set in the first instance. So as the gradient descent is working, the different filters are actually moving in different directions and detecting different features. If you set all the values to be the same, then you're quite right. It probably will be that all the filters will end up being the same. But if all the weights are set randomly, it would be highly improbable that they're all converged trying to do the same thing, particularly if the image has got lots of different things in it, which they could be converging on.
Okay, that makes sense.
Yeah.
So we apply the first set of filters, let's say 32. So their stride and their size of a filter need to be same.
Yes.
And we can stack them together.
Yes.
In the next stage, we apply another set of filters, which could be different. The dimension of the filter is different, as well as stride is different. And
Yes.
those can be like the stacked together.
Yes. Yes. So you get like one set of stack, and then something, and then maybe another set of stack, and then something, and then another set of stack. Because basically, I did say something in the middle, because these 10 filters that you've got, somehow they have to sort of you have to compute something which the next set of filters can apply on.
Correct.
So pooling is one of the things you can do,
yeah.
which is what will give you something that the next set can then work on. Yeah.
Okay.
Okay. So this is the stacking aspect. So this is so the reason why we need also the fact that all neutrons in a feature map share the same parameters dramatically reduces the number of parameters in the model. And this is So once the convolution has learned to recognize a pattern in one location, it can recognize it in any other location. And this is because the filter is doing the same thing across the whole image. So if it if the filter recognizes horizontal lines, it'll recognize it on anywhere in the image, because it's walking across the whole image. It's not applying to in one go on the whole image. It's taking these receptive fields at a time. So this is one of the nice features of CNNs, is that whatever pattern a particular filter recognizes, it'll recognize in different parts of the image. It doesn't just recognize it in one part of the image. And so there's this notion of channels, because images are not just black and white. So there's this additional, it just means that you've got extra, the filters have to be applied to the red, green, and blue. So you get even more outputs, because you get per channel the stack of filters being applied, not just to one image. They're being applied to the red, the green, and the blue separately. Yeah. Is that I'm kind of rushing over that, but is that clear, that this notion of channel in the image and then applying the full stack to each channel is needed because of the way things work? Or is that a bit confusing?
So we have, as we were discussing, like now we have 32, let's say 32 filters we are applying. Okay.
Yes.
So those 32 filters will get applied to RGB. So we're gonna apply those same set of filters to each channel. Is that correct?
Yes, that's right.
So that means that's 32 filters will produce 3 times the layers
Yes.
in a feature map 1. So
Yes.
when we say feature map 1, it's going to be RGB, that is 3 layers, multiply as many filters you have. That is your first layer of feature map 1.
Yeah, so they're not. You're quite right in terms of the number of things that are going to need to be done, but the channelness is kept like as a distinct as well. So that you'll have, for instance, the 10 outputs for channel 1, the 10 outputs for channel 2, the 10 outputs for channel 3. So that you can then apply at the next level another set of operations to channel 1, another set of operations to channel 2. So it's not that they all get kind of merged into one big lump of filter outputs. The channelness is kept in the network.
Oh, so that stack of feature map 1 will again have like as many filter you have applied, but
Yeah.
that set of 3 will stay as is.
Yeah, until you get to
So
pooling.
actually, it's not that set of 3 will not stay the same. Look how it works. You have some number of input channels. Let's say in case of RGB, we have 3 input channels. In this case, one kernel will be of shape, say 3 by 3 for the receptive field, and by 3, which is number of channels. So we have not a 2D kernel, but a 3D kernel, which is of shape of this kernel size by number of channels. And then we have a number of output channels. Let's say it's 16. So we have 16 of this 3 by 3 by 3 filters, which would output 16 features, like 16 2D feature maps. And in the next channel, we will have each filter of shape 3 by 3 by 16. And we will have, say, 32 of these filters of 3 by 3 by 16.
Okay. Okay, so you're saying they are kind of merged into one big lump of data.
Actually, it's like opposite of that, because we calculate, like we increase the number of channels when we go deeper into the network. But yeah, every feature map is calculated from all 3 channels at the first layer. So yeah, they are summed together.
Okay, so this is an example of what we've done here. So for instance, these are the 3 channels that we've got, and we've got a kernel that's being applied, and you've got maps created. And then, yeah, okay, so the different colors are being merged at level 2, because we've got green, purple, blue. So it seems like the channels here at this level are kept distinct, but then they start to get merged at the next level, because these are the input features. Yeah.
Actually, network can preserve channel separation if it's useful, because the number of output features is always at least the same as number of input features. So we can make a filter, a kernel, which would mostly react to the, say, red channel, if it's useful, like for a network to do its job. But that's not like any guaranteed or something.
Right. Okay. Okay, I give convolution connect to the outputs of the neuron in the previous layer. So this is to do with the stride across all feature maps in layer. Note that all neurons located in the same, but in different feature maps connected to the outputs of the exact same neurons in the previous layer. Okay. Okay, and so this is the kind of equation of how a particular neuron, this is in layer K, is computed from the original, the size of the height and width of the original input, as well as at a particular level based on the value from the previous layer times the weights on the current layer. So yeah, so this is kind of like the mathematical description of what we've just been kind of talking about as to how these are done. So I guess in some ways these guys are like really just features that the network treats these as a bit like we've got multiple features here. These are the features that the original inputs come. Okay. So it doesn't treat the channels really kind of like completely differently. It just treats them as if they were kind of filters, then identity filters applied. to the input. Okay. So yeah, because in this description, there's nothing special about it other than the fact that at a particular point, it's either looking at the input feature of a particular channel. Okay. Are people okay for time? Because it's already 7:40. I have a feeling the guys in the US will probably only come up to here as well, because there's a lot to unpack here. So the pooling probably will be done on Sunday. So we can probably join them for that.
Yeah, I agree. Yeah.
And yeah, so this is, well, I mean, I don't know if this is worth looking at, because this is a kind of hardwired filter, and the convolution applied to it. This is not using the layer code. So yeah, this was the example that they were showing above with the image. And this is one which is a 3x3, sorry, this is a 7x7 kernel with 3 channels. Because the image is, well, actually, it might only be 1 channel, because I don't know whether that's a color image or a black and white image.
Black and white.
Yeah, it's black and white. It'll probably be just 1 channel. And then here, what we've got is the third column is set to 1. So that's a vertical line. And here, the third row is set to 1, and that's a horizontal line. And they've applied the convolution to the images that they have as input, and then kind of plotted them out, which is what they showed earlier on, this effect of using a horizontal or a vertical line. So I think that's kind of okay. Yeah, there's a couple of parameters in the convolutional, which is the padding. So the same padding uses 0 padding if it's necessary, and valid is it drops the rows and columns it can't fit. In that it doesn't change the original data. It assumes it's valid data to use, and if it isn't, then it'll ignore some of the columns or rows at the bottom. And this is a kind of an example of where the padding, so that is being ignored because that's set to valid, and this is because this is a stride 5. So it's a 6 size kernel of stride 5. So when it kind of shipped over to there, it went onto that. But the next bit that we'll start to look at would be here, but there's no more data left here. So these are ignored because the padding is set to valid. And this is a slightly different one where the padding's been added, so that now it can still apply to that section because there's some additional data there that you can use as part of the calculation. And this is kind of just a visual representation of what padding's doing for you and why you need it. This is the actual convolution 2D layer in Keras, and this is the number of filters. So this is what we're talking about stacking. Here they've set it to a kernel size to 3, so it's 3 by 3, but you can have it different in one direction than another. They've set it here stride as 1. Again, you can have different strides in the different directions if you want, but here's 1 stride in both the X and Y direction. And the padding set to same, so it'll pad it if it's really necessary. And the activation function is ReLU. This is basically each filter is going to apply, this 3 by 3 kernel is going to compute the value, but then it's doing this non-linearity on the final result because it's going to be used in a neural network. So that's kind of the convolutional layer, what that represents. So here they're saying that you must choose the filter's height and width and strides and padding. So these are things, unfortunately, the stride, padding, and the height of the number of filters it is. These are not learned. You have to define these, unfortunately. But the actual weights within the filters, they will be learned. And yeah, there was a little discussion about memory requirements. You've still got. So basically, the reason they mentioned this is that during training, every single bit of data that the convolution is applying to has to be kept because the back propagation needs that to compute the gradient across all the different filters on the way back to modify their weights. Actually, I mean, they make a big deal about 1.2 gigabytes around. That's not a problem for most of us, but you have to be aware of the fact that during training, you will need a lot more data than during prediction, because in prediction, you don't need to keep intermediate values. They can all be thrown away, but unfortunately, during training, all the intermediate values need to be kept so that back propagation can work properly. and that's the issue. And they've got this thing where if it crashes, then try reducing the batch size and use 16-bit floats rather than 32-bit floats. So I think we'll probably stop there because pooling layers. We'll see. Hopefully the guys on Sunday will do those. Is that okay?
Yeah, perfect.
I don't know if anybody had any questions from what we've already read so far that was worth sort of going through before we just sign off.
It was good coverage today. Thanks for the question.
Cool.
Thanks, Ash.
Well, yeah, hopefully I'll see you guys on Sunday because yeah, I'm quite interested in this. Unfortunately, normally I can't make it, but I will this time. So yeah, have a nice week, guys.
Okay. Thanks, Ash. See you.
Right.